Yeah.
Yep.
Okay, so let's look at neon. Okay, so neon 20.180. Okay, so neon 20.180 basically is that number there. That's the atomic mass. So that's the atomic mass of neon, and it represents the average mass of all of the isotopes of neon. So there are three major isotopes of neon. You have neon 20, neon 21, and neon 22. 7 messages that I'm ignoring. Let me see if those are. So there's no lab today. Can you guys see my face now? Is that better?
Yes.
Okay.
Yeah.
And the test is not this weekend. It is next weekend. Yes. Okay. Okay, so as I was saying, there are 3 isotopes of neon: neon 20, neon 21, and neon 22. Now, this represents the average of all of those isotopes that occur naturally in nature. So what we're seeing here for all of the elements there, they're just giving me the isotopes that are occurring naturally in nature. And so as in a sense, we're taking the average of how much of it is there normally. So let me give you an example. We're talking about neon, right? So this is a mass spec of neon. It tells me, mass spec will tell me the relative abundance of neon compared to the other isotopes of neon. So here, this is about 90%. Of neon 20. This here, I'm gonna say it's probably like, I'm gonna say about 2% of neon 21. And so rough estimate, I'm gonna say about 8% neon 22. Okay, so we're gonna say that we're pretty much more exact than what we are, so that we can kind of keep enough sig figs to kind of make it work. So we're gonna say, fix these numbers a little bit. %90.00%. This guy's going to be 2.000%. And then this guy's going to be 8.00%. Okay?
How come the 2 has 3 zeros and the 8 has 2 zeros?
I'm just adding another one just for the hell of it.
Okay.
Because we're just taking guesses anyway, right? So we're just going to guess all the way around. I'm just trying to get a point across here. That's really what it is. Okay, so we're going to assume that this is 20.00000, enough so that we could have at least 4 sig figs. Okay, this is 21.0000, and then this is 22.0000. Okay, so what you would do to calculate the atomic mass, you would take the mass of that isotope and multiply by the decimal form of the percentage. So what is the decimal form of 90%?
0.90.
Okay, so we'd go 20. 20.00 times 0.90. Okay. And what is that?
18.
Okay. How many sig figs will we have?
2.
4.
4.
Okay, so 18.00. And it would be units. Okay, so that would be the first one. So now 21, getting ahead of myself, 21.00. So we have 2%. So then what would that be in terms of a fraction? I mean, a decimal.
0.02.
Okay. Okay, and that's going to equal
0.42.
I heard somebody say it, but I can't hear you. You said 0.42.
42.
And then how many sig figs?
4.
Okay. And then we have the last one, 22.00 times 8.00. So what would be that in terms of a decimal?
0.800.
Okay. And then that equals,
Do you have to add the last 2 zeros at the end of it, or does it matter?
yes, you would. Why?
I'm not sure. That's why I asked.
I'm asking the class in general. I figured you may not know since you asked the question.
Because we're doing sig figs.
Sig figs.
Because we're doing sig figs. And if you guys paid attention, for every question that I ask you that you don't take sig figs into consideration, you take the opportunity of losing 1 point. And so sometimes that's the difference between passing and failing. So you want to know sig figs.
It's 176.
So 1.76. Okay. So let's see if we can get these guys lined up.
Do we add that 0 after the 6 to make it 4 sigs? 4 6.
So how many sig figs do we have here? So we have 4 here,
4.
and we have how many here?
4.
4.
We have 4 here.
3.
We have 3 here. So then how many sig figs do we have?
3.
3.
Okay. So if I line these guys up and we add them together,
For the sig figs, how do you know which one to use? If the 22.00, if that one's 4 and the other one's 3, how would you know which one to use?
The smallest one.
there we go.
Okay.
Okay, so we got it lined up, almost. So where would I draw my lines?
After the 8.
After the 8, are you sure?
No.
0.
After the 0.
After the zeros. Okay, so this is going to be a little bit of a janky line. I apologize. So that's 1, 2. There we go.
Oh, wow, you weren't kidding.
Okay, it was like I was drinking. I told you. You're going to start wondering what I have in my coffee. Okay, so What about the next number? Where would I draw my line?
0.
After the zeros? Okay. And then the last number
After
After
6.
the 6.
after the 6, where the red one is. So which one am I going to use? Which line?
The first one.
Okay. So I can get rid of the green. Oops. Without, there we go. And then I'll add them up. So that's what? 0, 0. What is that? 8.
8.
And then
May have been
11.
9, no, 10.
is that right? So what am I going to use to determine if I'm rounding up or rounding down?
0.
0.
0. So am I rounding up or am I
You're
leaving it
leaving-
alone?
Leaving it alone?
Okay, so my answer should be 20.18 units. Or AMU, atomic mass. Both of those are acceptable. Okay, so neon.
Wait,
this
can you
will give me
repeat
the
that
average
again?
amount of, what was that?
What was acceptable?
Units
20.18 units and what?
or atomic mass units, AMU.
Are they interchangeable?
Yes, if you're talking about, so units can be used for, if you're talking about a compound, but if you're talking about an atom, it's atomic mass units.
So what would be preferred, like on a test? Units?
I don't have a preference. I'll accept both of them.
Okay.
So AMU is fine. Atomic mass units. It's fine. Or units is fine. Okay? Piece of cake so far? You get it, Hector?
Yep.
Yep. Okay, so how does this compare to what we got on our periodic table? What is on our periodic table for neon? What was the value for the atomic mass for neon?
20.180.
20.180.
20.180. Damn, we did pretty good. Right?
Yeah.
So that gives us an idea, right? So you get an idea of how much of each of those isotopes that are occurring in nature. So when we take a bottle of neon, which is a gas, right? And we take, let's say, a portion of it, we know that 90% of that is going to be neon 20. 21% of it is going to be neon 21. I mean, not 21%, 2% is going to be neon 21. And then 8% is going to be neon 22. So every time that I take neon and I break it down in terms of the percentage, I know exactly of how much each of those isotopes I'm incorporating in my reaction. You guys see that?
Yeah.
Okay,
Mhm.
good. So let's test out your skills. Here's the question. It says, the natural distribution of isotopes of boron is 19.9% boron 10 at mass of 10.012937 units and 81.1% boron 11 at 11.0093055 units. Calculate the atomic mass of boron. So what am I going to do?
You're going to multiply the percent by the mass?
Okay. So let's do that. So tell me what I'm doing. I'm a newbie. I don't know anything.
0. Is it 80? Do we? I don't know what you would do with the 0.1. Oh, it's that one. I was looking at the wrong one. Whoops, sorry.
Okay, so let's start off with that one. So what do I need to do? Now remember how this works. I look good, you guys do all the work. So help me out here.
0.199
Okay,
times 10.01 29730.
okay. How many sig figs would that be?
3.
Who's quick at the calculator?
9.
9 exactly? No numbers afterwards?
Sig figs?
Yes, sig figs. I need sig figs. How many
Oh.
sig figs would I need?
3.
Isn't it 3?
3.
Okay, 3 sig figs. And what would be my answer?
1.99.
A 1.99. Is that what you said? I'm sorry. I'm hard of hearing too, you know, old age. Okay, so 1.99. That's 3 sig figs. And then the next number? This guy here?
0.801.
Okay.
Wouldn't it be times 11.0093055?
Okay. And what do I get? How many sig figs am I looking for?
8,
3.
3.
3.
And wouldn't it be 8.01? Oh, wait, no.
Eight 8.82.
You said 8382?
8.82.
Okay. Okay, so we add these up. If we draw our lines, we only have one line, right? Not too hard.
10.81.
It'll be 10.8 because it has to be 3 sigs, no? 3 sig figs.
No, but when we're doing the addition, remember, we're adding the 2. So we just draw the line to determine. The line would be right here. But we don't have anything to determine if we need to round it up. So we just leave it the way it is. So in this case, it would be 4 sig figs because we did the addition way. Multiplication, if it's multiplication, 3 sig figs, right? But if it's addition and subtraction, we have to use the line. So that would be our answer. 10.81 units. How does that compare to boron on the periodic table? Let's see.
10 point. It's exactly.
It's exactly. So we're doing pretty damn good, right? That's 2. Man, we're on a roll. So it usually takes about two days because sometimes it gets backlogged for the videos. So, and then also I'm supposed to go through it and check to make sure what I said is what's in the closed caption. So I have to go through it as well. So it usually takes me about 2 days to sit there and get the videos up and running. But we usually have them up and running on my my page first. It may not be organized on the page, but it'll be on the video there first before we get them up on here. So, okay, on my channel. So subscribe to my channel.
Wait, you have a YouTube channel?
Yes, I have a YouTube channel.
For
I'll send you guys.
the lessons, right?
What was that?
For these lessons, like you're recording these lessons?
Yep.
Oh, okay.
Oh, there's a lot of other stuff on there too. Nothing bad, hopefully. Yeah. Okay, so naturally occurring lithium is composed of two isotopes, 7.59 at 6.0151224 and 92.41 at 7.0166. I'm sorry, I'm putting numbers in there like crazy. 7.016041 units. Okay, so what are we going to do? It says determine the atomic mass.
0.0759 times
0. Oh, let me type it because my handwriting is horrible. 0.0759, you said,
yeah,
times
6.0151224.
okay, and that equals how many sig figs?
4.
4.
3.
Oh yeah, 3.
3 is the correct answer. So what
Does
did you
it
guys
matter if we put the 0.0759 or could we just put 0.759?
get? You can put 0.0759, but I always like putting a 0 point in front. It just helps me visually. And keeps me from making stupid mistakes. Although I will promise to make a couple of stupid mistakes anyway. But that's neither here or there. Okay, so what did you guys get for your answer?
0.456.
0.457, right? Because it's 4, 5, 6, and then there's a 5, 4, 7 afterwards. So it's really this, right? It's 5, 4, 6, 5, 4, 7, 7, 9, 0, 2.
And we'll get like marked points if we don't round it or if we were to
Yep,
leave
if you don't round it, if you don't do your sig figs, you'll get marked points, yes.
Okay.
Okay, so I use that 5, and there's numbers following that 5, so I'm going to round up to 7. Okay, so that's the first part. Okay, what about the next one?
Multiply
0.9241
times 7.016
0.
0041.
Okay, sig figs.
4.
Okay, and what do you guys get?
6.48.
Okay. Is that 4 sig figs?
3.
That's only 3.
6.43.
3. Okay, so that's 4 sig figs. Okay, so when I add them up, where are my lines?
At the end,
Okay, at the end, so I only have one line to worry about. Oh, I like that. Okay, so what do you guys get?
6.940.
6.940.
That I got too.
Okay,
And we leave it alone?
and we leave it alone, 6.940 units. And we want to make sure to put our
Can we-
units. What was that?
Oh, I was just gonna ask if we could do like one more.
Oh, of course. I like it. You guys are hungry. I like hungry. Let's make it a little more challenging. This is too easy. Two numbers. Come on.
Is it okay if I got 6.94? Just
If
6.
you said,
I
is it okay if you
Yeah.
got 66.94?
No, 6.94.
6.94. Yeah, but you want to make sure that you have the same significant figures. The correct number of significant
So
figures.
after
Okay.
So you would need that 0 after.
after oh,
Because I'm going to dock you. Right? Dock you a point. Okay. Even though I slacked it, I would have got a point deducted from myself. So. Okay. So here's a table of some of the common naturally occurring isotopes. So let's actually do sulfur, something a little more challenging. So how would I go about doing that? You guys are going to work it out?
What did you ask again? Sorry.
Sulfur. So we want to calculate the average atomic mass of sulfur. Sulfur is S. So these guys. So how would I do it?
Multiply the percent by the mass for each one.
Okay. Let me make a white screen somewhere. Okay. So tell me what I'm going to do.
94.93.
Okay. Let me use a color that I can actually see at least. So 9493 times 3197. Is that right?
No, I think
Did I invert some numbers?
it's 9720.
Two.
You just forgot the 2.
Okay. So what do you guys? How many segments?
4.
Okay.
30.35.
That's what I got.
Okay. So. Okay. And then the next one.
0.076, I think. Oh,
Is that correct?
yeah.
So, okay. How many sig figs?
4.
4.
2.
Or
Oh, we have 2.
2.
Uh,
2 is
yeah.
correct. So
2.51.
Should be 2.4.
you said 2.51? Are
Would
you
it be
sure?
2.50?
Would it be 0.3?
Well, we got a lot of different answers going on there. Hold on, let me put it in myself. Then I'll tell you if I agree with you or disagree with you. 1, 4. I got 0.2.
2.5.
That's what I got.
Yeah, that's what I got too.
Uh-huh.
Okay. And then the next one. What is it?
4, 9,
0
0,
point
4, 2, yeah.
042.
Yeah, thank you.
Yeah, thank you. Am I getting food or money?
No, she came to drop something off for my sister.
Okay, so what did you guys get? How many sig figs?
3.
3.
Okay.
$1.45.
Okay.
Would it be 1.46?
I think so. 1.46.
You got 1.46.
Well,
So
it
why is
was
it?
457. But
Okay. Okay. And our last one.
0.0002.
Oops. Right. 0.2. There we go. Times 5 point. Oops. 0.9688. Okay. What did you guys?
It's 967080888.
9?
Oh, you messed up the last few numbers.
Oh, I did.
I think you read the bottom. This.
Oh, I read the wrong one. You're right. Oh, you're saying, yeah, I screwed up big time.
It's 9670.
See, that's why you got to keep an eye on me.
Take out the 8.
I put an 8 in there. Oh, another 8.
First one.
Yeah. Okay, I see it.
7. Yeah, 967088180. I don't think there's a 1.
No, it's
So I'm just making it all up.
Mm,
There you go. Is that good?
yeah.
See, that's why you're supposed to do all the hard work and I'm supposed to look pretty. Right? Okay, what did you guys get?
I got 7.193.
7.193? Are you sure about that one?
I don't know. Maybe I messed up. Let me just.
I got point.
I'm going to do it
Point
again.
0.0071. 7. 0.0072.
0.0072.
7.2.
Would it be 72 or would it be 7?
Just 7.
Just 7. Yeah.
Okay. Okay. So if we add these up, oops. Okay, so what do we get? Let's see, where do I draw my line?
The end?
The end of the first one?
Yes.
Right here.
How do
The end of the
you
last one. Oh yeah.
how do you know where to put the line?
Yeah, I was wondering.
So you go with the number of sig figs for that first number, right?
Mhm.
And then you go to the number of sig figs with that second number, and you see where you start losing significance, right? So this guy has 4 sig figs. The number that would be after that would be non-significant because it's not there, right? And then that's the same thing here. It would be the number that would be after the 5, which would be non-significant. Then here would be the number after the 6. And then here, this one here would be, if we drew the line there, it would be the number after the 7.
7.
Okay, so it would be right there. Okay, then we make a decision. Which one is the furthest to the left? The green line or the red line?
The green one.
Green.
The green one, right? And the reason that you use the one that's furthest to the left is because it's the number, it is the biggest number with the least significance, right? So it's not as exact as all of the other numbers are. And so that's why you'd use that line. So if we add this up, we get what? That's 7. 16. Carry the 1. That's 0.
2, 3.
1. Is that 32?
Yeah.
Yes.
And a decimal. Okay, so what am I going to use to determine whether I'm rounding up or rounding down?
The
7.
7.
32.07.
Okay, in units. That's it. Piece of cake.
Yeah.
That
So
wasn't bad.
it wasn't too bad.
I have a
No.
question.
Okay.
For I noticed the percentages, and then for when we write them out in decimals, how do you know exactly how much zeros to put into the
All you do is
percentage?
because a percentage means out of 100. So if you divide that number by 100, whatever the percentage is, then that'll tell you exactly how many zeros to put.
Okay.
Oh, so for
This is
the
divided by 100.
percentage, we always divide it by 100. Oh,
That's right.
okay.
Because it's 100%, right?
Yeah,
Okay.
I just
That's it.
did notice that because before. Yeah, you're right. Never mind.
Yep.
I'm not thinking.
Okay. So if you got a table like this on your exam, do you think you'll be able to utilize it to calculate the atomic mass of an element?
Yeah.
Yes.
Yeah. Yeah.
Okay.
Yes.
Piece of cake. Let's move on then. You guys got this. Okay, and that was the exact same example. Okay, so the periodic table is organized, right? And you notice that it's in numerical order based upon the atomic number, right? So we have 1, then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. You notice that?
Mm-hmm.
Okay, so it's organized based upon the number of proteins it has, right? But there's another way that we organize it as well, right? So the elements that are in group 1, except for that very first one, all these guys are alkali metals, right? All these guys are alkaline metals. These guys are all halogens. So they're going to behave the same way when they react. And that's going to be a very important part, which we'll talk about next week. Okay, but we may get into it this week. It depends how good we are. So, but the point is that they're organized. And if you notice, you also have numbers up here up top. So these A1, A2, A3, A4, A5, A6. So those guys are called your main groups. I'm sorry, 1A, 2A, 3A, 4A, 5A. Those are your main groups. So in the old days, when we didn't really understand transitional metals, which not to say that we are totally understanding of them because they're a hot mess, right? Transitional metals, these guys down here, we would ignore them. And so we would only focus on the main group metals. And so old periodic tables would actually have the main group metals. So now we basically use IUPAC notation. So our groups are just labeled from 1, 2, all the way to 18. So that'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, again, if you're in the same group, you're going to behave very similarly, okay? If you're in different groups, you're not going to behave similarly. You guys get that?
Yes.
Okay, so these guys are going to be your groups up top here, and down the side, you'll see, I'll show you on the regular periodic table, a normal periodic table. You excuse me. I'm going to talk too fast. So on a normal periodic table, we have what we call periods down the sides. So we have 7 periods. Okay, so we have groups up top, 7 periods. Okay, so we often use this for references, but it serves also in terms of levels, and it also helps us understand sizes of the atoms and stuff like that, energy levels and sizes. Okay, because they're organized in such a fashion that we can sit there and get energy levels from how they're organized, and also sizes of atoms on how they're organized. Okay, so it's important to understand that, and it's important to be able to find elements. So for instance, if I ask you to find palladium, excuse me, then not palladium, palladium, can you tell me what group it's in, which period it's in, its atomic number, and what type of element it is? I'll type it out. Okay? Yeah, I see it?
Yeah.
Group 10, period 5.
Okay. Okay, that's right. Group 10, period 5. Okay, so now tell me, what is this atomic number?
46.
Okay, that's correct. And what type of element is it?
Transition metals.
Okay. So let's see, what about selenium?
Group 16, period 4.
Okay. What is this atomic number?
34.
And what type of element is it?
Reactive nonmetals.
Okay. Does it have a special name?
Other nonmetals.
So non-metals. Does it have a special name?
Reactive.
Does it have any other special name? Like for instance, group 17 is called halogens. So what would group 16 be called?
Metalloids?
No, I don't know how to pronounce it. Chalcogens.
Chalcogen, yes. Okay, so let's see. What about, let's see, strontium? Strontium.
Wait, what? Which one?
Strontium?
Group 2, period 5.
Okay. So it's atomic number.
38.
38.
Okay. And what type of metal? I mean, what type of element?
Alkaline.
Metal.
Alkaline earth metals.
Okay. Piece of cake.
Yeah.
Yeah.
What's the 2A, 1A, 5B?
You said 2A, 1A, 5B.
Those, yeah, the small, like along the groups.
I'm looking.
'Cause, like I seen on the homework, it had like 5A group, whatever.
Okay, so hold on 1 second.
Like the previous one.
Mhm.
So remember, I told you earlier, these letters up here, the 1A.
Mhm.
So that 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So that used to be called the main group.
Okay.
So in the old days,
Okay.
we didn't understand transitional metals. So what we would do is ignore them, right? So we just pretend that they weren't there. And so we would just focus on the main group, and that was it. So
Okay.
chemistry back in the day, even before, actually it wasn't even before, because we used to use the main group all the time. We would avoid transitional metals. And so it wasn't until more recently that we started incorporating them into learning chemistry. Okay?
Okay.
Okay. So you're familiar with groups, periods, you know about the main group. And so often it'll say group 1A, right? And it'll say /1. So that's telling you, if you're old school, you would know group 1A. If you're new school, you'll know group 1. So you should be able to figure it out either way. So if you easily just ignore the stuff in the middle here, right? So it's like the valley. So avoid the valley, right? So when you're talking about the A series, the main group.
Okay.
Okay, so let's see. So if we're asking about the atomic number, list the atomic number, the chemical symbol, and the atomic mass of the third period element in group 16. Third period, group 16. Okay, any answers?
Sulfur?
That's right. And the symbol for it,
S.
is it a, what is it? It's atomic mass.
16. Yeah, 16.
16 is its atomic mass?
32.06.
32.06, that's correct. And its atomic number?
16.
16. And what type of element is it?
Non-metal chalcogen.
Okay, piece of cake?
Yeah.
Okay, good. So these are the most commonly used elements. So you want to definitely make sure that you know this. So my rule of thumb, at the end of the semester, if you come to me right before the final and I ask you, okay, so yeah, we're talking about carbon, carbon, carbon. And I said, so what is the symbol for carbon? And you tell me CR. I'm going to fail you on the spot, just so you know that, right? Because you should know by the time that you're taking that final, if you don't know what the symbol for carbon is, or you're not at least familiar or good enough to look at it up on the periodic table, then I'm definitely going to fail you right there and there. Okay?
Are you talking about just carbon or all of these symbols?
Well, it would be good if you know all of them, but you should especially know carbon, because we're going to be talking about carbon all the time. Do you know carbon, Kimberly?
Yes.
Okay, what is it? What is
I
the
don't know,
symbol
it's-
for carbon?
A C?
Isn't it? Oh,
That's
yeah.
correct. It's C. Okay? So you definitely want to make sure you know your symbols, right? Because if you don't know your symbols, it's going to be hard to do nomenclature. It's going to be hard to do chemistry in general. So you want to know them, right? And the reason why I give you guys the periodic table and I say you don't have to memorize them, because you should be looking at it daily. Every day, you should be looking at the periodic table, fondling over it, loving it, okay? It needs love. Kind of like plants.
Wait, so on our test coming up, we'll be able to use the periodic table, right?
That is correct.
Okay.
You said carbon is a whore, right?
Carbon is a whore. Did I show you the video?
Wait, what?
Did I show you the video?
No.
I didn't show this class the video?
Yeah,
No, I think you did.
you did.
Yeah.
Okay, so if I did, well, you can look it up yourself. It's called Chemical Party. And it'll be like, you'll see people in like gray suits or gray shirts and gray pants.
Yeah, you showed it to us.
Okay, so this is just showing you where a lot of those commonly used elements are at on the periodic table. And that's all for chapter 5. You ready for chapter 11? We're getting to the good stuff. Are you there?
Yes.
Chapter 11.
Yes.
Okay, so we got what, 10 minutes? See how much we can get done in 10 minutes. I think we can finish it. 11. Where are we? If I can find it. 3, 7. Okay, or at least the part that I want to go over today. So, all around us are basically electromagnetic radiation, or what we like to call it, since we don't like to think about radiation in a sense, electromagnetic waves, right? Energy is basically delivered to us in forms of electromagnetic waves, okay? So have you guys heard of gamma rays? Anyone?
No.
Yeah.
No?
I've heard of them.
Yeah.
Know what they are.
Anybody seen The Incredible Hulk?
Yes.
Yeah.
Yeah. So do you know why he's all green and built and muscular and all that stuff?
No.
He did something to
Gamma
himself?
rays.
Gamma rays, yes. So supposedly in the comics, he took in these gamma rays. So gamma rays are actually, they're electromagnetic radiation. It's a form of radiation. So, but they're very, 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 very tiny rays of light, right? And they're emitted as light rays, right? And the thing is that they have such a very small frequency that they're able to actually get into our DNA and destroy our DNA. So for us, it would actually destroy us if we got exposed to too much gamma rays, right? So do you guys take x-rays? Anybody taken x-rays recently?
I have.
Yeah.
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 What do they tell you about if you're pregnant? Anybody been pregnant and you had to get an x-ray at that time? No?
No.
Well, they try to tell you to avoid it because your baby is developing. And as that developing fetus, it's going to be very sensitive to x-rays, right? We're sensitive to x-rays too. Too many x-rays are bad. So, you know, occasionally they'll do it, you know, to check to see if you broke an arm or something like that, or if you go to the dentist, they'll check your teeth. But if you notice, they'll put a lead shield on you when you go to the dentist, right? So
Yeah.
that's also to
Yeah.
protect you from that radiation that's being emitted. Again, these are all forms of light radiation, okay? So how many of you guys cook?
Yeah.
Yeah.
I
Uh-huh.
do. Yes.
Okay, so I used to cook, but now I use the microwave, right? That's also a form of electromagnetic wave, right? So what is the new song on the radio? A really good song on the radio. Who's a good artist? What is your favorite song on the radio? They're like, radio, what's that?
I don't know. I have Spotify.
Excuse me. Well, back in the day, we used to listen to the radio. We always wait for the new hip and happening song. I heard that Doja Cat is something special these days. Is that true?
I guess.
You guess? Okay.
I don't even
Yeah.
know who that is.
I don't really like listen there, but
Okay. Okay. So radio waves, right? So those are all forms of waves. And believe it or not, they're all forms of light. So light waves all travel at the same speed, okay? So the difference between all of those different waves is either the wavelength or the density. I mean, not the density, the frequency.
Oh, I have a question.
Yep.
So, if I remember correctly, radiation differs between them because of how fast they go, I think is like the simple term, or like
No,
how
it's
much
not
they move,
how
and like that
fast they
determines
go,
if
because they're all going at the same speed.
like
Speed of light, right? So all of these waves are traveling at the speed of light, okay? And the speed of light is, but you're thinking along the right track. The speed of light is 3.008, or it's 3.00 times 10 to the 8th meters per second. Or if we go back to the empirical units, we put our chains back on, it'll be 186,000 miles per hour. Okay, so as scientists, we want to definitely use 3.00 times 10 to the 8th meters per second. Okay, so that is the speed of light. Okay, so I'm going to give you, and again, all of these rays and light is going to be energy, right? The way that we calculate energy, there's going to be a couple of equations. One of those, energy is equal to
MC squared.
H
No, MC.
times, and this symbol is called nu. H is Planck's constant. So that is a constant value. I can't remember the number off the top of my head, but it'll be given to you in the exam if we're asking you that. It's always going to be the same. Now, nu, and it's pronounced NU, nu. Nu is going to equal the frequency.
Dr. Henry, did you say constant or contant? What did you write?
Constant. That's a typo. Thank you.
Okay.
Good job. This is why I'm not an English major.
what's the little like thing symbol next to the H?
Nu,
New.
nu, NU, nu. So that is nu. So that's the Greek letter nu. Okay, and it means frequency. Okay, so if you look down here, this funny V, that's really supposed to be new. So it's supposed to be that funny looking like that. But it's hard to find on the keyboard. Okay? So now I want you to think about this. Now think hard about it. So if frequency is going up, now H is a constant, right? If H is a constant and frequency is going up, what's happening to the energy?
Going up?
It's going up. So the higher frequency you have, the more energy you're receiving, right? Okay, so keep that in mind. I want you to keep that in mind when we start talking about this a little bit more, okay? So another equation that we use is E equals mc squared. This is Einstein's equation. So where c is the speed of light, so this would be what you would use to calculate how much energy is given to you for the speed of light if you knew the mass of the particle. All right. Okay, the other equation for energy, we have E equals 1/2 mass times velocity squared. So if we shot Martin out of a cannon, we can calculate how much energy he's going to have when he hits the ground by using that. Because we know how much Martin weighs, we can calculate how fast we shot Martin out of that cannon, so then we can calculate the amount of energy. You guys get that?
Mm-hmm.
Okay, so along those same lines, if I had a coffee cup and I got really mad at Vivian and I threw it at Vivian, right? What is going to have more energy? If I really give her all my force or if I just toss it?
Oh, your force.
Your force.
Or
Fire force.
Okay, so you guys get that too. So it's going to be proportional, right? Okay. So directly proportional or indirectly proportional?
Directed.
direct.
Okay, good. Piece of cake, simple so far?
So far.
So far.
So far, okay. Okay, so the last part that we're going to talk about, and then I'll show you a figure, and then we'll stop at that point. Last part I want to talk about, speed of light is equal to lambda times nu. Okay, so again, this is nu for frequency. So the speed of light, which is always going to be the same number, what is the speed of light?
180.
0.00 10 times 8, 10 to the 8th power.
That's correct. Okay. So that's always going to be the same. So the only thing that's going to be changing is either your frequency or your wavelength. Lambda means wavelength. This is the Greek letter lambda. Okay. So wavelength, you guys have been to the ocean, right?
Yeah.
Okay. So at the top of the wave, and then as that next wave to the top of the other wave. So that's called peak to peak. Let me draw my wave. So from here to here, right? That distance between those two peaks, that's called your wavelength. Okay? So wavelength and frequency are indirectly proportional. So as the wavelength goes up, the frequency goes down. So like radio waves are long, we could have long radio waves. Have you heard of the long radio? Right? So the reason why they call it the long radio is because it has long radio waves, where gamma rays have short wavelength. So if gamma rays have short wavelength and radio waves have long wavelength, which one is going to have more energy?
Can you repeat that?
The longer wavelength?
Okay, it's I asked you if gamma rays have a short wavelength if I can spell, and radio waves have a long wavelength, which would have more energy?
Radio wave? The short wave?
The short ones. The short wavelengths.
Okay, so the answer would be the short wavelengths, because based upon our equation, if we have short wavelengths, that means our lambda is small, that means our frequency is high. So if we take that frequency and we plug it into here, that's going to give us a larger value for energy. So what does that mean? That means that the energy is indirectly proportional to the wavelength. So as energy goes up, the wavelength is smaller. So remember I told you, I said gamma rays, they're so small, the waves are so small that they go in and they break up your DNA, right?
Yeah.
They have more energy. Did you guys get that?
Yeah.
Yeah.
Okay, so let me show you my figure and then remind me that this is where we stopped last time. Okay, so this is the electromagnetic spectrum. So as you can see, on the electromagnetic spectrum, we have up top, we have frequency and we have wavelength. As we go from left to right, is frequency increasing or decreasing?
Decreasing.
Yeah, decreasing, that's correct. As we go from left to right, is wavelength increasing or decreasing?
Increasing.
Increasing.
Increasing. And you can actually see the waves, right? So here's your gamma rays. Look how close they are together, right? And then here are your radio waves from peak to peak. Look at that. Look at that distance. And this gives you how big they are relative to real things in life, right? So for instance, a dog, right? A dog is right at the point where we start FM radio waves, right? So the distance of a dog from head to tail, that's about the size of the wavelength. Okay, so that's pretty big. And then down here for X-rays, an atom. So the size of an atom, which we can't see with our eyes, right, would be the distance of an X-ray, the wavelength of an X-ray. So that kind of gives us relatively how wide those waves are. Okay, you guys get that? Piece of cake?
Yes.